Topic of polynomial functions is one of the most interesting topics in all of mathematics. Now, we've discussed linear functions before. We've talked about sort of a standard form for the linear function, the slope-intercept form, if you recall, and a general form for the linear function. We've also talked a bit about quadratic functions. Now, in the previous chapter, we talked about some transformations, rigid transformations first, where we moved left and right, up and down. We changed the equation or the function a bit, and we saw how those changes in the function caused changes in its graph. Then we talked just briefly about non-rigid transformations, where a change in the function caused a change in the shape of the parabolic curve. Let's pick up our discussion sort of where we left off, and even do a little bit of reviewing here before we go on. Consider f of x as x squared, and this is its graph. Recall that if we have another function, g, let's say, that's x squared minus 3, it is simply the f function. This is simply f of x minus 3, you see. It's all of those vertical distances, but down 3. So it makes sense that the graph moves down our coordinate system 3 units and looks like this. Another transformation was one that went left and right. And we're tipped off about that movement because we see an operation on x before the squaring operation, before the prevailing operation involved in our function. Now, this kind of movement is in a direction that we said we don't expect. That is, if we see x minus 3, we end up moving the graph 3 places to the right on our coordinate system. So this is where the graph ends up. Now, notice it's the same shaped parabola as we had originally, the same as f of x is x squared. Suppose we have another function here, and we put the two ideas together, both kinds of transformations, that is left, right, and up and down. X plus 2, since that operation is occurring before the squaring operation, we know that the motion is horizontal. And the negative 1 occurring after the squaring causes the graph to move down our coordinate system 1 unit. All right, so the x plus 2 moves the graph 2 places to the left, the negative 1 place down. Now, earlier we chose a convenient point on our parabola, and we chose the vertex. The vertex of f of x as x squared is here at the origin. And if we think about where that vertex is moving, we'll understand where all of the points on the graph will move. So this vertex is moving 2 places to the left and 1 position down, so the vertex ends up here. Now the graph is pretty easy to imagine. The graph then looks like this. Now with parabolas, we have been referring to this point as the vertex. You know, if the parabola opens up like this, then the vertex will be the lowest point on the graph. A minimum, you see. And if, of course, it opens downward, it would be the maximum point on the graph. Well, another aspect of parabolas is that they have this symmetry notion. Now, we talked about symmetry earlier as being a condition that is related to the x and y axis. Well, here with the parabola, imagine a line that goes through the parabolic curve like this. You see, right through that vertex. This then becomes a line of symmetry. So our axis of symmetry, or our line of symmetry, goes through the vertex. And sometimes this line is simply called the axis. Well, let's move now to non-rigid transformations. Changes in the function that would cause a change in the very shape of the parabolic curve. We talked about, a function like g of x is 1/2 x squared. Now, we think about this in comparison to the f function from earlier, f of x is x squared. If this is the x squared function, then 1/2 x squared means that the vertical distances being described here are 1/2 the vertical distances in the x squared function. So, for example, for this x value, we have that vertical distance. If we take half of that vertical distance, then we're describing a point that's on that function. If we take, now understand, I'm regarding this as the f of x is equal to x squared, the graph of that function. You know, so if I want 1/2 x squared, I'm just taking vertical distances that are half as long. For this x value, the vertical distance is this long, and if I take half of it, you see I'm describing a point on this graph. So what's happening is that multiplying by a fraction that is between 0 and 1 turns out to cause the graph to take on a shape that's a little fatter than the regular shape of the parabolic curve. In a similar way, we can see what would happen if we defined a function that's 2 times x squared. You see, these vertical distances are twice the vertical distances involved in the x squared function. Now, here's our x squared, so if I'm talking about this point, then for the 2x squared, I'd be defining a point that's twice as high, twice the vertical distance. For this x, you see, twice the vertical distance would move it up here. The notion is then that when we multiply by a number that is larger than 1, we'll end up causing the parabola to take on a shape that's relatively thin relative to its normal shape, you see, something like that. Now, consider what would happen if I defined a function that was the negative of x squared. You see, it's like these vertical distances are nothing more than the negative of the vertical distances involved on the regular parabolic curve. Well, all of these y values then are the negatives of the ones in the regular function. So it would simply cause the graph to open downward. Well, this leads us to some generalities here. We can put all of these ideas together into one function like this. Now let's decide where this vertex is, the vertex of the graph of this function. And of course all of the other points will move along with that vertex. Well, the regular parabolic curve has its vertex here at the origin, so we're moving from the origin. Now the x minus 3 occurring before the squaring causes the graph to move left and right in a direction we don't expect. We see negative 3 or minus 3, it's going to move to the right 3. Now, the plus 1 moves it up 1. All right, that puts the vertex here. Now, the 2, this 2 plays the same role as those factors just a moment ago played. That is, the 2 is causing the graph to move up our coordinate system faster, twice as fast as the normal curve. So it's going to cause the graph to take on a shape which is relatively thin. So now we understand that the graph opens up and it's relatively thin. If this were negative 2, it would open downward and be relatively thin. Okay, so just sketching the graph then, I'll sketch a relatively thin parabolic curve using this point as my vertex. Now, a couple of things to notice here. The vertex is at the point 3, 1. And this vertex point can be seen by looking at the function written in this form. You see, here's the 3, there's the 1. Now notice that the 3 is a number that follows a minus sign here. Also notice that the axis of symmetry for this particular problem would be this vertical line. Now if we examine this situation using a number of constants, a, h, and k, you see, if we can put our function into this form, we will have identified the most important aspects of its graph. That is, we'll know that we have a vertex at the point hk. Now notice that h is a number that follows a minus sign here. The a is telling us a number of things about the shape of the graph and the direction or in which way the parabola opens. A determines up or down. That is, if A is positive, the graph opens up. If A is negative, the graph will open down. Now, if A is a number whose absolute value is between 0 and 1, it turns out that the graph will end up being fat. That is, if it's a normal fraction, you see, either positive or negative. A fraction between 0 and 1, positive or negative. The graph will be relatively thin if that A value is larger than 1 or smaller than negative 1. And the graph will be relatively regular or normal in shape if A itself is 1. Also, we'll have an axis of symmetry, or an axis at the line x is equal to h. You see, x is equal to that h. That'll give us a vertical line, you see, going through that vertex. Well, now we've come to the point where we have been exposed to the general form of a quadratic function, which is this. F of x is ax squared plus bx plus c. And now what we've just looked at is a standard form, a form from which we are given aspects of its graph. So the standard form, f of x is a times x minus h squared plus k. Next, we'll investigate a method of going from the general form to the standard form so that we can generate the graph of a function that's given to us in general form. Suppose we want to take this function and change it into its standard form in order to construct the graph that's involved here. Well, let's see. Here's how we proceed. Now, you know what we're aiming to do is create a situation where we have a binomial squared and then we have plus or minus some constant. Well, does it make sense that what we'll need to do is complete the square? And to do that, of course, we'll think about it this way. We'll take the existing constant, move it to the side just a bit. Now we're viewing the problem like this. We're going to reinvent this constant term so that we'll have a binomial squared. That's completing the trinomial square. All right, now I'll leave that step in there just for emphasis for the time being, because what we're doing to complete the square is we're taking 8, taking half of it, and then squaring that amount. So what we'll write in this vacant area will be half of 8 squared. That's 4 squared. Now I'll write it as 4 squared here, just for emphasis. But notice now we're adding 4 squared, or 16, to this side of the equation. I'll bring down this 11 for now. If we're adding 16 to one side of the equation, in order to keep the equation balanced, we have to do one of two things. We have to also add 16 on the other side of the equation, or we have to undo this operation on this side of the equation. Now, since we want f of x to be isolated on the left side of the equation, we're really not going to operate over on this side. That is, we don't want to show that 16 is added on the left side. We'd rather keep our operations confined to this side of the equation. Now, to think about it like that, since we're adding 16 here, we'll subtract 16 here in order to maintain the balance of our equation. All right, now notice what we get. Factoring, we get x plus 4 squared. Now, I left the 4, I wrote this as 4 squared instead of as 16 here because it's important to notice how the factoring occurs. All right, now collecting out here, I get negative 5. Now I understand that this graph is going to move to the left 4 and down 5 on our coordinate system. The important thing here we want to emphasize, though, is not so much the construction of the graph, but the method of going from a function that's in a general form into the function in its standard form so that we can graph. All right, let's look at another one. Now, in this one, notice that we have a coefficient here other than 1, and we're going to look at how we deal with that problem. We might begin our procedure the same way. That is, we'll start by clearing our existing constant, just moving it out a little bit perhaps, and thinking of the problem like this. Now, we want to reinvent our constant term in here, but we notice that in order to complete the square, this leading coefficient needs to be 1. Now, to make it a 1, what we'll end up doing is force the factorization of that constant through this binomial. Now, notice that we don't have to force the factorization of the 2 through all of the terms involved in our original function. We only have to force the factorization of 2 in the binomial part here. That is, we'll write it this way. 2 times x squared plus 4x. And then outside of the parenthesis, we have that constant that we kicked away earlier. All right, now let's complete the square in the parenthesis. Half of 4 is 2. 2 squared is 4, so we'll add 4 in here. Now, I'll go ahead and write the 4 this time, but we understand that it's 2 squared, and we know what the factorization is going to be. What we intend to do next is undo what we did here. We're adding 4. Now, the first thought might be, well, what we need to do is subtract 4. That's not exactly the case, though, because we have a 2 factor out here. Although we're adding 4 in parenthesis, what we're really doing to the equation is we're adding 8, you see. It's 2 times 4 that we're actually plugging into this side of the equation. So if we're adding 8 in here, we have to subtract 8 in this region in order to undo what we did here. All right, so the important thing is to take under consideration this factor that is involved with our parenthesis. Okay, now let's continue the factoring process. This becomes x plus 2 squared. Now I know it's 2 because 2 is the amount squared to give 4. And then out here I'll collect to get the negative 3. Now I have placed, taken the function and we have gone from the general form to the standard form, and now from the standard form we could easily imagine the graph. Well, let's think about that a little bit. The graph, you see, it's the regular parabolic curve except justified 2 to the left, 3 down, and it's going to be relatively thin, you see, and it'll open up. Up because this is positive, and thin because this is a number larger than 1. Now the vertex, you understand, is at negative 2, negative 3. Now that's rather important. To emphasize where that vertex is located, I might think about, whether I write this or not is unimportant perhaps, but I'm going to think about the problem in this way. This will help me identify the location of the vertex. You see, if you're simply looking at the function and identifying a vertex, it's commonly mistaken that you simply use the number that occurs here without regard to sign. Well, you're actually looking for a number that follows a minus sign. So if it's plus 2, you think about it as minus negative 2, you see, and identifying the number that follows the minus sign, it would be negative 2. Now, another way to view the position of the vertex is to think about the transformation that is involved here from our standard form. The plus 2 in here is indicating that we move left or right in a direction we don't expect. So we're moving to the left 2. You see, the x movement is minus 2, and the y movement is negative 3. Okay. Also from this one, another aspect that we could point out is that we have an axis of symmetry that is a vertical line that goes through at negative 2. So that axis is at x equals negative 2. X is negative 2 for every y. So we have a vertical line going through here. Well, one more. Suppose we have h of x is negative 3x squared plus 18x minus 25. Now again, we'll begin by thinking about separating the existing constant. Kick it out just a bit and think of the problem more like this. Now our concentration is in the parenthesis. We're looking to complete the square, so we'll force the factorization of negative 3. Now I'm saying that we force this factorization because it doesn't make any difference whether this number divides that coefficient or not. We have to factor this negative 3 out of whatever that is. All right, let's see. We'll factor the negative 3 out of these two terms, and we have x squared minus 6x, and the negative 25 just comes down. Now we're ready to complete the square within the parenthesis. Half of the negative 6 is negative 3. Negative 3 squared is 9. So we're adding 9 in here, or 3 squared. Now, notice although we're adding 9 in parenthesis, what we are really doing to this side of the equation is negative 3 times 9, you see, which is negative 27. We're really subtracting 27 here on this side of the equation. To undo the subtraction of 27, we have to add 27. Now we're ready to complete the factorization. We have the negative 3 times x minus 3 squared. Now, know it's negative 3 here because it was negative 3 that was squared to give the 9. All right, and then collecting the negative 25 with 27, I get plus 2. I know then that the vertex will be at 3, 2. The vertex of this graph will be at 3, 2. The graph will open down because this a value is negative, and it will be relatively thin because this is a number that's greater than 1 without its sign, or its absolute value is larger than 1. Here's a problem in which we are going to find the equation or the function whose graph has certain characteristics. It says to find the quadratic function having a graph that passes through the point 2, 3 and a vertex at 0, 2. Now, let's just get the big picture of where we're going with this. We have had a function in general form, and we've gone to standard form and the graph. You see, we're operating mostly in that direction, from the equation to the graph, equation to the graph, equation to the graph. Well, we need to be able to go the other way as well. That is, aspects about the graph can give us the equation or the function, and that's what we're about to do here. Now, it might make some sense that the close correlation is between the equation in standard form. You see, the function that's in standard form and the graph. So the standard form is what we're going to be working with here mostly. We'll understand what we have. Let's see. It says that this graph goes through the point 2, 3. And just sketching it right quick here, here's the point 2, 3. And it has a vertex at 0, 2, about right here. Okay, so the graph then looks like this. All right, well, not a lot to go on, it doesn't seem like, but let's just write down our standard form and see what we might do. What we understand at this point is the position of the vertex, certainly, and the coordinates of the vertex are represented by the h and k here. So let's replace within our function that information. We have a times x minus, now the h part is 0 squared, plus the k is 2. Well, that's not quite enough. We need some other replacements. We need to find the value of a mostly. And all we have to work with are the coordinates of a point. Well, that's quite enough, because you see, the relationship between points on a graph and the function itself is that every point on the graph represents an xy pair that makes the equation or the function true. So we can do a replacement here. This is an xy pair that causes that equation that we're building to be true. Now here's the x part. F of x can be written as y. We can replace this with y, and this xy pair can be represented by this x and y. All right, so let's do that. We'll have 3 then is equal to a times 2 minus 0 squared plus 2. Now what we're really doing here in replacing x and y for numbers or with numbers is we're actually going to find the value of a. Well, let's see, we have 3 is equal to, this is 4a plus 2. Now I'll subtract 2 on both sides. I'm about out of room here. Let's go up here. Subtracting 2 on both sides, I'll get 1 is equal to 4a. A then, dividing on both sides by 4, a becomes 1/4. Well, what do I have? Let's go back to the standard form. F of x is a times x minus h squared plus k. All right, then f of x, I know what a is. I just found it to be 1/4. And I have x minus, now the h and k were given earlier as 0, 2. Well, let's see. I can simplify this a bit further as 1/4 x squared plus 2. So this then is the function that goes through the point 2, 3 and has a vertex at 0, 2. Here's an interesting problem. The path of a diver is given by this relationship. Y is equal to negative 4/9 x squared plus 24/9 x plus 10, where y is the height in feet and x is the horizontal distance from the end of the diving board in feet. Now, understand what the relationship is saying in terms of the diver. The diver takes a path that is parabolic. Now, y stands for the vertical distance of the diver, you see, at any point along the path, and x is the horizontal distance, just like with our coordinate system. Well, what we aim to find out here is the maximum height attained by the diver. And let's not only find that out, let's find out the maximum height of the diver, but let's find out how far from the end of the board this diver is as well. Now, doesn't it make sense that if he is tracing a parabolic curve, that point will simply be the vertex of this parabola? You see, so all we need to do is identify the h and k in the standard form for this function, this quadratic function. All right, so h and k. H will give us the height of the diver. K will give the distance from the end of the board. Well, in order to do that, what we'll do is take our equation, our quadratic equation, and place it in the standard form. And to do that, we'll begin this way. Now, notice what I have done here is I have forced the factorization of negative 4/9 out of these two terms. And I have moved the plus 10 out, and I'm considering the problem like this. All right, the negative 4/9 out of this term leaves x squared. Negative 4/9 out of this term, you see, leaves negative 6. And we can verify that by understanding that negative 4/9 times negative 6 would give plus 24/9. All right, let's pick up the problem from that point. Now we want to identify the new constant, which we generate by taking half of the negative 6 and squaring. All right, half of negative 6 is negative 3. Negative 3 squared is 9. So I'll be adding 9 here. Now, adding 9 means I'm really doing what? I'm really doing what is implied by the product here. Negative 4/9 times 9, the 9's mentally cancel, and I'm just subtracting 4. You see, I would get negative 4 when I multiply these two. So if I'm really subtracting 4 on this side, I need to add 4 out here. Okay, let's go to the factored form. I've got x minus 3 quantity squared, and 10 and 4, 14. So now my vertex is at 3, 14. Now 3, remember, that x portion was the distance from the end of the board. How far away from the board has the diver gone? And 14 is the height above the board that he has attained. So 3 feet from the board, a height of 14, and that's the maximum height attained by the diver. Now, you know, if we were going to do a lot of problems like this, that is, where we needed to find the vertex of the parabolic curve, and that's often the case when you talk about a shot putter or a javelin thrower, and we want the maximum height and the distance attained for that maximum height, or we want how far the object is going to be tossed, or a rocket and the maximum height of a rocket. All of those kinds of problems involve the same kind of operation, and that is taking a general form and moving to a standard form. Well, perhaps there's a faster way for us to get the HK, the coordinates of a vertex. We can examine that by taking a function and simply going through the process of going into the standard form. Now, here's how we would proceed. And notice what I aim to do is kick out the C and look at these two terms and force the factorization of A. All right, let's force the factorization of A. I would have A times x squared plus B over A times x. And I'll move the C out here. Now notice I'm forcing the factorization of the A, and we can verify that this is the correct factorization by multiplying A times B over A x to get bx. You see, the A's would cancel, and I'd be left with this. All right, now I want to identify the amount that I'm going to to place in here as my new constant term. And that amount is half of b over a squared. So I'm going to add half of b over a. Half of b over a, that's b over 2a. So this is b over 2a squared inside here. Now what amount, you see, what amount am I actually adding? I'm adding a times that, you see, to this side. So I have to subtract a times b over 2a squared. All right, let's go through and simplify just a bit. This is a times x plus the amount squared is b over 2a, and that gives me a neat way to factor this. You know, all of my activity is out here, I believe. I've got plus c, let's see, minus a times b over 2a all squared is b squared over 4a squared. Now I see a cancellation with the a's. Let me run through and rewrite. And as I do, now begin to identify the h and k, the identity of the vertex. You see, because here I'll have c minus. Now these a's go out, and I'm left with an a down in the denominator. So this is b squared over 4a. Now my h and k, the h is here, the k is all of this. You see, so in terms of the vertex of a general, from a general form, I've got a vertex at b over 2a, and the y component is c minus b squared over 4a. And maybe this seems like an awful lot of work, but it could make, if you had to do it many, many times, it could make life just a little bit easier. All right, so my vertex, just to overemphasize it, is at these positions. I should say this position, because these are the coordinates of a particular point. Now, let's go to our previous problem and see if this information would have helped us. You see, in our previous problem, here's the A, the B, and the C, all right, from our general form. Now, if I take this information and plug it into that information that I had over there, then I could generate the 314 point perhaps as easily as I could by doing this. And if I had 20 problems to do, I would just want to plug in that A, B, and C information rather than having to go through the factorization that we had to go through over here. This one didn't turn out too bad because we had some convenient fractions to work with, but these can get awfully ugly as the problems get more complicated. With quadratic functions and linear functions, we have a way of changing those functions into some standard form. And the standard form tells us some aspects about the graph of those various functions. Well, when we get to functions of higher degree, we don't have a specific standard form from which we construct a graph. But we do have a way of understanding what the graph will look like. And that understanding comes from a series of tests and procedures. And it's kind of like going to a doctor and getting a physical. You know, what the doctor does is he does a number of tests and procedures on his patient, and then from the interpretation of those tests and procedures, he understands something about your general health. Well, let's begin this series of tests and investigating the kinds of things that we're looking for with the first test, the leading coefficient test. Now, the leading coefficient test is based upon this fundamental idea. And by the way, we'll be using mostly a point plotting method to discover the behavior of graphs of functions of higher degree. Now, that may seem like a long procedure, and it really is, because if the graph is very curvy, you see, we would have to plot an awful lot of points to tell the behavior of the graph. So we just need some procedures and some things to look at to help streamline that process, to help us understand aspects of it. Okay, here we go. The leading coefficient test is based upon this idea. If we're building our table of values and we choose values of x that are particularly high, particularly big, either positively or negatively. Look at what happens to the function. That is, look at what happens if we replace a number like 10 in place of x. Now, here we would have 10 to the 5th power. Now, 10 to the 5th power, that's a 1 with 5 zeros, you see. That's 100,000 times 2. This term becomes 200,000. And 10 to the 4th power is 10,000. Negative 7 times 10,000 is negative 70,000. Now, the point here in comparing these two amounts is that the number, the value of our first term, is overwhelming this second term. And as a matter of fact, by choosing an x that is sufficiently large, this first term will overpower all of the other terms combined. So to be able to tell how the graph behaves at the extremes of the coordinate system, which is what the leading coefficient test is for in the first place, all we need to do is take x's that are sufficiently large, or just think of numbers that are very, very big, and evaluate only the first term of our function. And we'll be able to tell how the y value, or f of x, changes as a result, and be able to tell how the graph behaves. Here's what I'm talking about. Think about what happens if x is extremely large. You see, x to the 5th will be extremely large. Positively, I'm talking about. 2 times that positive number is a big positive number. This big positive number will overwhelm all the rest, so we don't even have to consider those. And we understand then that y will be a big positive number when x is a big positive number. That tells us that as x gets bigger, 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 the y values get bigger, 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 you see. And so the graph will exit the coordinate system upper right. Now, in a similar way, we can tell what happens to the left of 0 along the x-axis and in our coordinate system. You see, imagine x as being a big negative number. A big negative number, raise it to the 5th power. Raise a negative number to an odd exponent, we get a negative result. 2 times that negative number, this number is negative. Big negative. So f of x, or the y value, will be a big negative number. That tells us that as the x's get bigger and bigger negatively, you see the y value is going to get bigger and bigger negatively, so the graph will ultimately leave the coordinate system lower left. Now, all we're doing is, by a little bit of logic, determining how the graph behaves at the extremes of the coordinate system. Now, let's just change our first term just a little bit and see what kind of situation would result. Suppose we have a negative 2x to the 4th power. Let's see how this graph will behave at the extremes of the coordinate system. Just imagine now what happens if you put in a very big x value. A big positive number for x raised to the 4th power, that number's positive. Negative 2 times that big positive number, negative. These don't matter. F of x, or the y value, then is negative. So as x becomes bigger and bigger and bigger positively, then the y values become big negatively, and the graph will exit the coordinate system down to the right. Now imagine big negative x's. Big negative number. Raise that negative number to the 4th power, it becomes positive. This positive number times negative 2, negative. F of x, or y, will be big negatively. So this graph will exit the coordinate system lower left. Now, this procedure requires nothing more than a little logical thought. It doesn't require any memorization, and that's very important here. There are a number of procedures that we're going to be talking about, and mostly they should be simply understood and accepted in terms of their concept, more so than some memorization process. All right, let's talk about another item here. Suppose we have this function. Now, we can determine the behavior of this graph, or at least in part, by performing a factorization. Now, what the factorization will do, of course, is allow us to identify the x-intercepts. Now, here's the factored form, and the x-intercepts are at the points where the x is causing each of these factors to become 0. This factor becomes 0 when x is 0. This factor becomes 0 when x is 2. This factor becomes 0 when x is negative 1. Now, the whole idea of identifying the x-intercepts, you know, is based upon the idea of letting y, the f of x here, be equal to 0. And the values of x that cause each of the factors to be 0 causes this to be true, so we have our x-intercepts. Often this step would not have to be written, just thought of, you see. All right, so these are the x-intercepts. Now, that is, they would be at the point 0, 0, at the point 2, 0, at the point negative 1, 0. As such, they can be put into the table of values. Now, these x-intercepts are also called zeros. They're called zeros because they are the positions along the x-axis where the y becomes 0. They are also called solutions because they are solutions in this particular equation, you see, when the function is put into this form. And a couple of things are important here. It's important to notice that the x-intercepts or the zeros or the solutions can give us points to plot on the graph, and rather important points as well. Also, I believe it's important that if we know that 2, for example, is an x-intercept or a 0 or a solution, if 2 is a 0, then x minus 2 is a factor. Think about the problem sort of in reverse, because it'll occur here shortly where we may be able to identify zeros without factoring, and as a matter of fact, by identifying a certain 0, we'll be able to determine a factored form. So just notice that if x minus 2 is a factor, then x is equal to 2 is a 0. But if 2 is a 0, it also implies that x minus 2 is a factor. All right. Let's plot these points on a coordinate system and look at some other things. 0, 0, 2, 0, negative 1, 0. 0, 0 is here. 2, 0 is here. Here's negative 1, 0. All right, now notice just by plotting these points, we don't know a great deal about the behavior of the graph. Notice this, though, that we started with a third-degree polynomial function. And we have what apparently is going to lead to 3 crossings of our x-axis. It is the case that the degree of the function corresponds with the maximum possible number of crossings of the x-axis. If we have a 5th-degree function, you see, it can cross at most 5 times. Now, suppose we have 3 crossings here. Think about how that can occur. It can occur from upper left, we have a crossing, and then back through this point, and back through this point, and out of the coordinate system. Well, if we have 3 crossing points, we can have at most 2 turns in our graph. The graph comes down, it turns here, it turns again up here. You see, so we have 2 turns in the graph if we have 3 crossing points. The number of turns of the graph is 1 smaller than the number of crossing points. All right, our leading coefficient test here can help us decide how the graph will exit the coordinate system and allow us really to do a rough sketch of the graph. Let's see. Up here, the leading coefficient test now would mean examine this leading term. All right. If this number is large positively, a large positive number cubed, big positive number. So as x gets big positively, the y value gets big positively. The graph exits upper right in our coordinate system. If x is big negatively, cube a negative number, we get a negative value. So as x gets big negatively, y gets big negatively, and the graph exits lower left. So our graph is going to do something like this. It's going to come down here. Now what we don't know is how far this will dip down, but we know we'll have a turn here because we need to go back through at this point, come back up, and again, we don't know how high this goes, but we know it'll turn back and exit lower left like this. Okay, so this is just a rough sketch of the graph. To get a better idea of the behavior of the graph in this region of the graph, we might do f of 3. We might do f of 1. We might do f of negative 1/2 to see roughly how high the graph gets in this region. Roughly, I say, because it might not be the exact point where it reaches its maximum. Okay, so notice now 2 turning points, 3 crossings. Consider this graph. Now, we're going to look at 2 things in conjunction with one another and recall some of the things we talked about earlier. In this function, if we perform the factorization, we get x minus 3 squared. Now, we understand that the value of x that causes this factor to become 0 would be 3. That is, we'll have an x-intercept, imagining f of x or y being 0, and solving for x. Then we understand that x needs to be 0 for that to be for this to be true. All right, so the point 3, 0 is an x-intercept. Now notice that we have two factors of x minus 3. So this is an x-intercept, we might say, of multiplicity 2, or this is a solution of multiplicity 2. Now what happens in a situation like that is rather predictable. I mean, we have seen the quadratic function before. We understand from our idea of movement of the graph of a quadratic that this will be a normal parabolic curve justified 3 positions to the right of the origin on our coordinate system. And actually that vertex is at this position. So here we have the vertex, and the graph looks something like this. Now, the main point of this little discussion is that if we have a factor that occurs twice, that is, the exponent on a factor is 2, that instead of having a crossing point at this x-intercept, we get a bounce of the graph. We get a bounce off of that point. Now look at what happens if we have a factor of multiplicity 3. Notice now x plus 2 cubed. The x-intercept then will be at the position where the value of x causes this to become 0 when f of x is replaced with 0. So x would need to be negative 2. So the x-intercept is at negative 2, 0. And this point, this negative 2, is called a 0. Now what happens? Well, we understand from our previous work about transformations that this will be the normal f of x is x cubed function, a little curvy function, which looks like this, by the way, this thing, only it is justified 2 positions in a direction we don't expect. So it's going to move 2 over to the left on our coordinate system. It looks something like this on the coordinate system. Now, the point of this discussion is that if we have a factor that's cubed, then the behavior of the graph through that x-intercept will be more like this cube function idea, where it comes down and it gets relatively flat in this region of the x-intercept, and then it goes back out. Now, let's put these two ideas together into one function. For example, suppose we have a function that is structured this way. Suppose we have, let's call it a g of x, and some of the factors of g of x are these. We have x minus 3 squared. We have x plus 2, let's say, cubed. You see now, if we expanded this would be a cubic polynomial. This would be a squared or quadratic polynomial. Multiplying those two, we would have an expanded polynomial function of the 5th degree. So we have a 5th degree function. We can have at most 5 crossings, at most 4 turning points. But in this case, we have factors that appear several times each. 2 factors of x minus 3, 3 factors of x plus 2. Now, how does the graph behave? Well, here's all we have to do. Now, identify these x-intercepts, the value of x that causes each factor to be 0. For this one, we have an x-intercept at 3. Now, what we understand about that is that the graph will behave according to a quadratic function. That is, we'll get a bounce off of that point. Now, all we have to do is determine whether the graph is coming into the coordinate system from lower right or upper right to understand how that bounce operates. In this particular one, the graph will come in like this, and it'll bounce off of that point and go back up. Now, we don't know how far quite that it will go up at this point, but we could investigate that by finding f of 2 and f of 1 and f of 0 and so on. You see, we could get some points to plot and have a better idea of the behavior of the graph. The point of the discussion, though, is how does the graph behave in the region around these x-intercepts? All right, what about the x plus 2 cubed? Well, the x-intercept here is at negative 2. The negative 2 causing this factor to be 0. So at negative 2 we have an x-intercept. Now the behavior of the graph in this little region of the graph is just like the cube function. You see, what will happen is the graph will go up here some distance, come back down, and then it'll flatten out sort of right through here, and then go down again. Now, you might be asking, gee, well, what about if this were a 4 or a 5 or a 6 or a 7? Then does the behavior change and change and change again? Well, no, it doesn't. A fourth degree situation right here, an exponent of 4, would have the same fundamental pattern as this pattern, except the graph would be just a little flatter in this region. You see, it would start to form more defined shoulders here. And if it was to the 6th power and any higher even power, those shoulders would simply be more defined. You see, and we would get a turning very rapidly here, and the graph would rise more rapidly out here to the right. In a similar way, if this were a 5 or a 7 or a 9, all we get is the flattening of the graph through this region. It will form a little shoulder here and be further out this way, you see, and over on this side as well. So, but it's the same fundamental pattern that we get with the squaring and the cubing, and that's the main point here. Consider this function. F of x is negative 2x to the 4th plus 2x squared. If we can put the function in the factored form, then we can identify the x-intercepts, therefore the zeros, and we can begin to construct the graph. Well, factoring, I'll take out a common factor here of negative 2x squared. Coming out of this term leaves me with x squared. Negative 2x squared out of this term leaves just simply negative 1. Now, the difference of squares here factors into x minus 1 times x plus 1. So the zeros, the values of x that cause each factor to become 0, would be 0 for this factor, 1 for this factor, and negative 1 for this factor. All right, now look at what this looks like on a graph. X is 0, that's here. X is 1. X is negative 1. Now, part of the behavior of this graph can be found by doing a leading coefficient test. Let's do that. Up here in the original function now, if x is big positively, then that big positive number raised to the 4th power is a large positive number. Negative 2 times that positive number makes this term negative, and therefore f of x or y will be negative when x is a big positive number. What that tells us is that the graph comes into our working area of the coordinate system from lower right. All right, so it'll come in like this. Now notice that x is equal to 1. That's a 0. The point 1, 0 is an x-intercept. And it is a factor here. X minus 1 is a factor only once. That tells us that the graph is going through this point. All right, now, presumably the graph will make a turn here at some point and then come back down. Now, what happens here? Now, notice we have a choice here. Does it go through that point and then back up through this point, or what happens at that point? Well, let's see. Since 0 is a factor, you see, twice here, it has that x squared composition. So we're going to have the behavior of the graph in this little region of the graph that is similar to the parabolic curve. That is, the graph is going to do something like this. It's going to come down and bounce from that point and go back up. And then it's going to come back and go through this point. So the graph is going to look something like this. Now, I know the bounce occurred because this is a 0 twice, you see. So we get a bounce off of that x-intercept or off of that 0. Consider this situation. Suppose we want to find a polynomial function with the following zeros. Okay, we're building the function, you see, from some aspect of the graph. The zeros, x equals 3, x equals negative 2, and x is equal to 0. Well, we understand from previously that if 3 is a 0, or if 3, 0 is an x-intercept, then x minus 3 will be a factor. So we can build our function this way. Let's call it the g function. If 3 is a 0, then x minus 3 is a factor. If negative 2 is a 0, then x plus 2 is a factor. If 0 is a 0, then x itself is a factor. Okay? Or I could say this is x minus 0, but x minus 0 is simply x. So this product then, if I wanted to write the function in expanded form, I could do this kind of thing. X minus 3 times x plus 2 is x squared minus x minus 6. And then multiplying times x, we would get x cubed minus x squared minus 6x. Okay, a function that has these as zeros. Consider this one. 3x to the fourth minus 4x cubed. All right, factoring. A common factor here is x cubed. Extracting x cubed from both terms, we get 3x minus 4. Now again, the zeros. There's a 0 at x equals 0, and another 0 where x is 4/3. Now I'm thinking about that. I figured that out like this. I figured that out by thinking of what value of x causes this factor to be 0, and we can think through it this way if we wish to do so. What makes 3x minus 4 equal to 0? Well, 3x is equal to 4, and x is equal to 4/3, you see, solving for x. All right, that's how we can think through that part, but these are our zeros. These are our zeros. Graphically, then, we have an x-intercept at this point and an x-intercept at 4/3, which is 1 and 1/3, roughly right here. Now, how does the graph behave? Again, the leading coefficient test would tell us some information about that. Leading coefficient test. If x is big positively to the fourth power, big positive number, 3 times that positive number, positive value. The y value is positive then when x is big positively. That means that the graph comes in from upper right. All right, so the graph then will presumably come through this point. Now notice I know it goes through the point because 4/3 is a 0. This factor is a factor only one time, you see, so it'll go through that 0. All right, now what happens here? Well, we're going to make a turn back, and do we go through this point? Do we bounce off of that point? How does the graph behave around this 0? We can figure that out by looking at the exponent on x here. This is a factor of multiplicity 3, so it's going to have the behavior of the x cubed function. That is, it's going to get kind of flat in that region of the graph. In other words, the graph will come down like this, it will turn back, and it will have the behavior of the x cubed function. It's kind of in reverse right here, but it gets flat near this 0 or this x-intercept, and then goes back up, continues to go back up again. The intermediate value theorem, although it looks imposing, is a rather simple concept. The real-world analogy to the intermediate value theorem is this. Suppose a farmer goes out in the field and observes that his sugar cane is 2 feet tall in March, let's say. And then he returns in November to find that it's 6 feet tall. Well, it makes some sense that at some point in time between March and November, the sugar cane was exactly 4 feet tall. And on another day, it was exactly 3 feet 3 inches tall. And for that matter, there was a time, some day during that period, when the sugar cane was any height between 2 feet and 6 feet. Well, that's the whole idea of the intermediate value theorem mathematically. That is, if we're dealing with a polynomial function, and remember that polynomial functions are continuous, there aren't any breaks in the function. So if we know that the function behaves this way, let's say in this part of the coordinate system, that is that, let's say f of 3 is 1, 2, 3, 4, and that f of 2 is 1. You see in the graph behaves something like this, let's say, and goes out of the system. That the graph will take on every value between 1 and 4. That is, given any, there must be an x between 2 and 3 such that f of that number x will give every number between 2 and 4. That is, the graph is contained in here somewhere. We don't know how it behaves. I don't know, maybe it runs like this a little bit. It wiggles just a little bit. That's okay. The idea is that for any y distance, there exists an x within this interval such that f of that x will give me that y value. Okay, now that idea, that is seemingly obvious idea, allows us to understand that if we have a function like this, graphically, let's say, where we have f of 1 to be, let's say, negative, and f of 2 is positive, then it must be the case, you see, that there is a crossing, that there is an x-intercept between 1 and 2. And we don't know it precisely where it is, but we know it's in there. And in order to approximate that crossing, if we can't factor to get at it, perhaps you see it could be an irrational number between 1 and 2. So, but to get very close to it, to approximate it, what we can do is this. Just take half of this interval over which we know we have a crossing. Take the midpoint. All right, now find f of that midpoint. Let's say f of 1.5 is this number, is negative. Now notice that we know that we have a crossing between f of 1.5 or we have a crossing between 1.5 and 2, because f of this end of the interval is negative and f of that end of the interval is positive. F of 1 1/2 is negative, f of 2 is positive. So we must have a crossing within this interval. So we split that interval. We take f of that x, and let's say f of that x is positive. All right? If that is the case, then you see we have an interval here, and f of one end is positive, f of the other end of the interval is negative. We must have a crossing within this interval. Split that interval. You see, and by continually performing this iteration, this splitting of the interval, and taking f of the midpoint and deciding where, in what interval we have a crossing, we can approximate the actual zero to any degree of accuracy that we care to choose by continuing to split the interval, split the interval, split the interval. As an overview, think about what we've been doing. We have been taking a function and building a table of values that we plot on a coordinate system to discover the behavior of the graph. If we can factor our function, we can identify x-intercepts, and those add to our table of values and add to our understanding about the behavior of the graph. Well, this process involving factoring and identifying x-intercepts and building the table of values is one which becomes more complicated as we are less able to factor our polynomial function. That is, when the polynomial function becomes a little more complicated, it's a little more difficult to deal with. Now, we need a little bit more efficient method of factoring our polynomial, identifying zeros, and evaluating the function at some x. You see, besides just plugging values into our function, our polynomial. It turns out that there is a method, and that method is tied into a process called synthetic division. Now, synthetic division is what we want to talk about here. Before we do, and before we look at all of the ramifications of synthetic division and how important it is to this study of polynomial functions, let us just start with this idea. We're going to build on synthetic division now, and we're going to talk specifically about factoring first. But think about this. Suppose we say in this polynomial function that 2 is a 0. Now, from our earlier work, we understand that if 2 is a 0, then x minus 2 is a factor. Now, if x minus 2 is a factor, what is the other factor? Well, to find the other factor, and to factor this polynomial into x minus 2 times some leftover, That's the process that we want to get at. That's where synthetic division will help us a great deal. Now, to study that idea, does it make sense that if I know that, for example, 3 is a factor of 12, to discover the other factor, I can go through the long division process. I can say 3 into 12, you see, goes 4 times. And now I know that 4 is the other factor. So I can factor 12 into 3 times 4. All right, using a similar kind of logic, if I know that x minus 2 is a factor of this polynomial, then I can simply divide x minus 2 into that polynomial, and whatever number I get up here as the quotient, you see, the quotient times the divisor is equal to the dividend. All right, so let's go through the process. Now, this long division process follows nicely the general idea of division which we understand from the past. By the way, this is not synthetic division. Synthetic division comes from this, but we need to show this first. All right, let's see. Here's how we proceed. We take the first term here of the polynomial that we're dividing into that one, the first term into the first term here. That's how we begin. X into 6x cubed goes 6x squared times. Now, I know it's 6x squared because 6x squared times x is 6x cubed. You see, now I'm discovering my dividend, or excuse me, my quotient, and I'm multiplying this piece of the quotient back times the divisor. And that's what we do in normal division anyway. 6x squared times x is 6x cubed. 6x squared times negative 2 is negative 12x squared. Now notice that when I'm placing the term 6x squared up here in my quotient region, that I'm placing a term of it above a term of the same degree. You see, the squared term is here, I place a squared term here. When I multiply back, I'm putting the terms of the same degree below one another for a specific purpose here. All right, now, our prescription in long division would be to draw a line and subtract. Once we multiply through, we draw a line and subtract. Now, what that means here for polynomials is it means this. I'm subtracting this amount from that amount. Now, subtracting means subtracting. That's a negative 1 times each of these terms. It implies then a sign change. So let me write the sign change like this. This is really, see, that sign will change to plus. Now, what we usually do in this process, instead of showing that minus and parenthesis, we simply say, and here's what we had before, we simply say, change the signs and collect. So here, the 6x cubed would become negative 6x cubed, and the negative 12x squared would become positive 12x squared. Now, to emphasize the fact that we're changing the sign, often what we'll do is put a circle around the sign that's there and then change the sign below or perhaps above. Now, in doing that, we're emphasizing that we have changed the sign, because forgetting this is a common mistake. Now, sometimes this is placed above. All right, so here's what we have. The 6x cubed minus 6x cubed, they go out. They add out as expected. You know, the multiplication here was set up so that it would be identical to that term. All right, so that's going to be a trivial operation each time. Now here, the negative 19x squared with plus 12x squared gives us negative 7x squared. All right, after we have done the subtraction, we bring down the next term. That's this 16x. And we begin the process again. X into negative 7x squared goes negative 7x times, because negative 7x times x is negative 7x squared. Then negative 7x times negative 2 is plus 14x. We draw the line and subtract, which means that we change the signs in this polynomial and collect. Now, changing this sign, you know, showing that sign change, the negative 7x squared plus 7x squared, they'll go out as expected. And we won't even deal with this first term in the future because it's a trivial operation. It's a very predictable thing. All right, the most important part is right here. Change the sign, now collect 16x minus 14x, 2x. Now we bring down the next term. We bring down the next term, the constant, and we begin the process again. X into 2x goes 2 times. 2 times x is 2x. 2 times negative 2 is negative 4. We draw the line and subtract. Of course, this sign change and collection is trivial. This sign change and collection turns out to be 0. Our remainder is 0. That means that our division went evenly. That means that since x minus 2 divides this polynomial evenly, and this is our quotient, it means that the quotient times the divisor will give this dividend. Well, this has become then a way of factoring our function over here. And let's look at that. That means, back over here, that we could rewrite our function as, see, we know that x minus 2 is a factor. We know that the other factor involved in that polynomial is the quotient over there, 6x squared minus 7x plus 2. All right, so this is a way of factoring. Now, just to enhance our understanding of this long division process, let's understand this. Suppose in this problem the division did not come out evenly. Let's just suppose that we had, let's change this to, let's say, negative 1. And what would have been brought down here would be negative 1. Then the collection here would have produced 3. Now, since the division didn't go evenly, we could not have done the factoring that we implied over here. My point of this discussion, though, is to show what our complete answer is. You see, here we have a quotient with a remainder of 3. Now, what happens in normal long division when the division doesn't come out evenly? Let's see. What if I have 3 into 11? You see, 3 into 11 goes 3 times. 3 times 3, 9, with 2 left over. So we write this, we put the remainder over the divisor, you see, and just tack it on to the whole numbered part in our division process. So we say this is 3 and 2/3. 3 and 2/3. It's really 3 and 2/3 like this, and we're used to writing it as 3 and 2/3 this way. But it's really 3 plus 2/3, you see. We read it as 3 and 2/3. Now, in this process, we will simply take the remainder and put it on top of, or make the fraction with, the divisor and add it to the end of this part of the quotient, because this is not a complete answer, you see. The complete answer would be 6x squared minus 7x plus 2 plus remainder over the divisor. You see, that then is the complete answer in this division process. Okay. That isn't what we had. We had a 4 here, and we had a 4 here, and 0 as our remainder. Well, let's see what synthetic division is all about. Now, I'm going to leave the important parts of this division process here. That is, here's what we're thinking of when we divide. And here was our answer. Now, synthetic division is simply a shortcut of a particular kind of long division process. What we're doing in synthetic division is we're trading in the operations of dividing and subtracting, which is what division is all about. We divide one thing into another, we multiply and then subtract. And then we divide again and multiply and then subtract. Well, the division and subtraction parts of that process are more difficult operations than multiplication and addition. So the synthetic division process simply trades in the harder operations of dividing and subtracting for the easier operations of multiplying and adding. And here's how it works. In dividing by x minus 2 in long division, synthetically it's simply the division by 2. And we'll set the division up like this. Now we're dividing into, it turns out that we don't need the variable parts of these terms. We only need, and the only important part here would be the coefficients and the constant. So let's write down the coefficients and the constant. That's all we need in synthetic division. And here's how the process works. We bring down this first item, the first number written in this group of numbers. Just bring it down. Now, we proceed this way. 2 times 6 is 12. Now, collect these. Just add them. The negative 19 with 12, negative 7. Then, go again. 2 times negative 7, negative 14. Add these, we get 2. Then 2 times 2 is 4. Negative 4 with 4 is 0. And this number is the remainder. Now, the numbers, the other numbers that appear here, are simply the coefficients and the constant involved in our polynomial answer. Now, notice our answer was 6x squared minus 7x plus 2. 6x squared minus 7x plus 2. Now, to identify the degree of the polynomial answer, we just simply understand that the degree of our answer will be 1 degree smaller than the polynomial we divided into. We divided into 6x cubed, a third-degree polynomial. Our answer is going to be a second-degree polynomial. So this will be 6x squared minus 7x plus 2. And the remainder is 0, so we have nothing more to write here for our answer. Okay, so we have, in synthetic division, we're trading in the operations of dividing and subtracting for operations of multiplication and addition. Well, let's consider the process a bit further. Suppose we have 5x cubed plus 6x plus 8. Now, we're leaving the function notation just for a moment, just to understand the synthetic division process. In dividing by x plus 2, you see, as a polynomial, synthetically, we divide by negative 2. And we're dividing negative 2 into the coefficients and the constant involved in this numerator polynomial. Now, it's important to write down a coefficient for every degreed term that is involved in the polynomial. Now, notice here we have no second degree term. So we can think of this as 0x squared, you see. And in our synthetic division process, we'll put the 0 as a placeholder for the squared term, for the coefficient of the squared term. So we have 5 and then 0x squared, and then 6x, and then the 8. All right, let's run through the process. Bring down the 5. Negative 2 times 5, negative 10. Together, negative 10. Negative 2 times negative 10, 20. Together, 26. Negative 2 times 26 is negative 52. Together, negative 44. Now, notice that we have a remainder in this particular problem. These are the coefficients and the constant involved in our, it's sort of like the whole numbered part of our answer, and the negative 44 is the remainder. The proper and complete answer here would be 5x to an exponent that's 1 less than that. You see, so it's 5x squared minus 10x plus 26 plus the remainder over the divisor. So it's plus negative 44 over the divisor, which is really this binomial, you see. We were dividing by x plus 2 synthetically. So here's our complete answer. Take a look at this function. F of x is 5x cubed plus 6x plus 8. Suppose we want to find f of negative 2. What we would need to do at this point is replace the x's that are in the f function with negative 2. So this x becomes a negative 2, that x becomes negative 2. We bring down the 8 and we evaluate. We perform indicated operations. Negative 2 cubed is negative 8. 6 times negative 2, negative 12. 5 times negative 8, negative 40. Collecting here, we get negative 4. Together, we get negative 44. Notice that f of negative 2 is negative 44. Now let's notice what this function is, what this polynomial function is in regard to what we just did. Look over here. 5x cubed plus 6x plus 8. Now, we divided that polynomial, which is the function we were just talking about, by x plus 2. We did so by dividing by negative 2. All right, synthetically. So we divided by negative 2 synthetically, and look at this. The remainder is negative 44. And we found over here that f of negative 2 was negative 44. The synthetic division by negative 2 gave a remainder which was negative 44. Now, the importance of this is that the synthetic division process is useful in evaluating a function at a certain value of x. Evaluating the function at a certain value of x. That's a fast way of building our table of values. We often have to do that in our polynomial functions. And as the functions become more and more complicated, the value of the synthetic division process grows. Take a look at this fourth degree function. Now, its f of x is 2x to the fourth plus 7x cubed minus 4x squared minus 27x minus 18. Now, what we are going to do is discover some aspects of the behavior of the graph and actually construct a graph here. Now, as we do that, we are building a table of values. Now, let's set up a table here and begin our process. We begin by finding f of 0. Well, that's pretty easy just by observation, you see. We can have a look at putting the 0 in place of this x and 0 in place of that x and 0 in place of this x, and each time the term will go out. 0 in place of that x. Well, all that's left then is the negative 18. So f of 0 will simply be negative 18, constant. Well, what about f of 1? Well, we can find f of 1 using our synthetic division process. And dividing synthetically into our coefficients and the constant here, we would have 2, 7, negative 4, negative 27, negative 18. Now notice that we're not missing any terms. That is, we have a term for every degree from 4 down to 0. So we don't have to add any placeholders here. That's an important thing to look for when doing synthetic division. All right, the process looks like this. Bring down the 2. 1 times 2, 2. 7 and 2, 9. 1 times 9, 9. 9 with negative 4, 5. 1 times 5, 5. With negative 27 is negative 22. 1 times negative 22, negative 22. And together here we get negative 40. That means that f of 1 is negative 40. Let's try 2. Now again, we're dividing into the same coefficients and constant that we talked about earlier. So I'll just write them down here, copy them down, bring down the 2. 2 times 2, 4. 7 and 4, 11. 2 times 11, 22. 22 minus 4, 18. 2 times 18, 36. 36 minus 27 is 9. 2 times 9, 18. 18 with negative 18 is 0. Oh, happy day, we've run into a 0. That is, f of 2 is 0. So we can put the point 2, 0 into our table of values. 2 then is an x-intercept. And most importantly here, we have a factor of our polynomial. If 2 is a 0, then x minus 2 is a factor. So here's what we understand. We know then that f of x has as one of its factors x minus 2. And the other factor is found right here in the synthetic division process. It is given by the entries at the bottom of the synthetic division. Now remember that the polynomial being described here is 1 degree smaller than the polynomial we were dividing in originally. So this is a third degree polynomial function or polynomial that's being described here. So this will be then 2x cubed plus 11x squared plus 18x plus 9. Now we would continue the process of investigation. Let's go to the negative side now. Let's try negative 1. dividing negative 1 into the original function, and I'm dividing into the original function because if my division doesn't come out evenly, I want to make sure, well, whether it comes out evenly or not, I want to put the point negative 1 and this remainder into my table of values. And I can't do that if I'm dividing negative 1 into these factored forms. All right, let's see. So negative 1 into the 2, 7, negative 4, negative 27, negative 18. All right, bring down the 2. Negative 1 times 2, negative 2, together 5. Negative 1 times 5, negative 5, together negative 9. Negative 1 times negative 9, 9, with negative 27 is negative 18. Negative 1 times negative 18 is 18. Aha, again, a remainder of 0, which means that f of negative 1 is 0, or that negative 1 is a 0. So f of negative 1 is 0, and that those coordinates can be placed into our table of values. And we know now that x plus 1 is a factor of the original polynomial. All right, if x plus 1 is a factor of the original function, it's also a factor of any equivalent form of the function. So it's a factor here. Now, it's either a factor of that factor or it's a factor of this factor. Clearly, x plus 1 cannot be a factor of x minus 2. So x plus 1 is a factor of this factor. Now, how do we discover the other factor? That is, how do we complete this factorization? See, we know that x plus 1 is a factor of this, has to be, but what's the other factor? Well, we can find out by using synthetic division. You see, the negative 1 divided evenly synthetically into the original function. It is bound to divide evenly into the factor that it is a part of. That is, we know that x plus 1 is a part of this factor. So the synthetic division will give us the information we need about this other factor. Let's see how it works. Now I'm dividing into this factor, so I'll use 2, 11, 18, and 9. 2, 11, 18, 9. Bring down the 2. Negative 1 times 2, negative 2. 11 with negative 2 is 9. Negative 1 times 9, negative 9. Together 9. Negative 1 times 9, negative 9. Together 0, as expected. We knew this remainder would be 0. What we're after here are these entries. You see, this gives us the information to fill this in. The 2, the 9, the 9. That's 2x squared plus 9x plus 9. Now we're on our way to a completely factored form. Now once we get down to a situation where we have a quadratic factor, we proceed using the methods that we have previously learned. That is, we just factor this quadratic factor using our normal methods of factoring. Here, for example, we would factor this way, thinking of this as, let's see, the product of two binomials. 2x squared is probably 2x times x. And all signs are plus, so I have plus plus here, factors of 9, 3, 3. And let's verify the middle term. 2x times 3 is 6x. With 3x, that gives 9x. The middle term is verified. The factorization is correct. Well, in a completely factored form like this, or in a form where we have a series of binomial factors, we can then identify all of our zeros or our x-intercepts and discover a lot about the behavior of the graph. All right, we know that our zeros then are at x is equal to 2, at x is equal to negative 1. We've already entered those into our table of values. We have another 0 at x is equal to negative 3/2, and we have another one at x is equal to negative 3. So this tells us that we have intercepts at negative 3/2 is negative 1 1/2, and at negative 3. Now, let's see what this information tells us about our graph. Well, on a coordinate system, let's plot some of these points. The point 0, negative 18. 0, negative 18. Well, 18 is somewhat off of our graph, so let's just put the a point down here as a reference point. We may be thinking that we're using tiny y units, you see, and we'll come down here a distance and put the negative 18. 1 goes to negative 40, that's even further down, so let's just put it down here somewhere just as reference. Then 2, 0, negative 1, 0, negative 1.5, 0. Those are pretty close. Negative 3, 0. Now, how is the graph behaving? Well, we understand that we started with a 4th degree polynomial function, and we have 4 intercepts. Therefore, since none of these zeros occur or give binomial factors that are factors more than one time, the graph is clearly going through the x-intercept. You see, as opposed to bouncing off of or becoming flat at that point, something of that nature. Now, we know also by the leading coefficient test that the graph is coming into the coordinate system from upper right and it's exiting upper left. So here's what's happening. The graph comes blasting in like this, and it comes down to a point somewhere in the neighborhood of negative 40 here. Now, we're not claiming that this is exactly a relative minimum point here, but it's probably near that point. Now, I'll treat it as a minimum at this point. But, you know, the graph could go below the negative 40 over here and come back through the negative 40. There are some procedures, some relatively simple procedures in calculus that would allow us to identify the exact position of this minimum point. You see what x corresponds with that exact minimum point, and what is that minimum y value. All right, at any rate, we come down here, the graph is going to come up and go back through the point negative 1, 0. It's going to come up here some unknown amount of distance and then turn back, go back through. And we didn't do negative 2. We could have done an f of negative 2 here to find out exactly where it crosses in this region of the graph. But it will come down some distance, make a turn, and come back up this way and go out of the coordinate system in that fashion. Well, the point of this whole discussion had to do with synthetic division and its value in discovering the aspects of the graph of a more complicated polynomial function. Now, the synthetic division did 3 very, very important things for us. It was allowing us to find f of some x. You know, just looking at the remainder in our synthetic division process, we understand that we're finding f of that number that we're dividing synthetically by. And in doing that process, we can identify zeros. And in identifying zeros, we can perform a factorization. So it's helping us to find the functional value at a certain x, it's helping us to identify zeros, and it's helping us to factor. So those are important tools in our quest for the behavior of the graph of a polynomial function.